Inferential statistics. Inferential statistics involve a decision-making process that allows us to estimate population characteristics from sampled data. The success of this process requires that we make certain assumptions about how well the sample represents the larger population. These assumptions are based on two important concepts of statistical reasoning: probability and sampling error. Probability is a complex but essential concept for understanding inferential statistics. Probability is the likelihood that any one event will occur, given all the possible outcomes. We use a lowercase p to signify probability, expressed as a ratio or decimal. For example, given the two possible outcomes for the flip of a coin, the likelihood of getting tails on any single flip will be E1 of 2, or 0.5. Therefore, we say that the probability of getting tails is 50%, or p equals 0.5. The example on the slide can be found on page 406 of your text. This concept can now be applied to a distribution of scores. Suppose we had access to data for height of all adult men alive today. This distribution of millions of scores would approximate the normal curve. Suppose, too, that the mean height was 69 inches with a standard deviation of 3 inches. Now, what if we select one man at random from this population? What is the probability that the man will be between 66 and 72 inches tall, or within plus minus 1 standard deviation of the mean? We know this range represents 68.26% of the population as shown by the center green area in figure 18.1. This means that approximately 68 or 100 men can be expected to be between 66 and 72 inches tall. Therefore, there is a 68% probability, p equals 0.68, that any one man we select will fall within this range. Similarly, the probability of selecting a man 78 inches or taller, scores beyond plus 3 standard deviations, is 0.0013, as this area represents 0.13% of the total distribution as shown by the gray area in the tail of figure 18.1. It is important to understand that probability is predictive in that it reflects what should happen over the long run, not necessarily what will happen for any given trial or event. Hint: think of surgical risk. We use probability in research as a guideline for making decisions about how well sample data estimate the characteristics of a population. We also use probabilities to determine if observed treatment differences are likely to be representative of population differences, or if they could have occurred by chance. This brings us to sampling error. The estimation of population characteristics from sampled data is based on the assumption that samples are random and valid representatives of the population. Even when truly random samples are used, we cannot be sure that one sample's characteristics will be identical to those of the population simply because fewer cases are included in the sample. Here's an example. Let's say that for the population of babies, the mean birth weight is 120 ounces with a standard deviation of 5 ounces. If we sample 10 babies, the mean birth weight is 115 ounces with a standard deviation of 30 ounces. What accounts for the difference? Random sampling implies that all members of a population have an equal opportunity of being chosen, but obviously, this does not guarantee proportional representation of all parts of the population. If we were to choose another 10 babies, it is not likely that we would obtain the same value for mean and standard deviation as the first sample. The laws of chance tell us that through a process of infinitely repeated random sampling, we should expect to see such differences among the sample means. The tendency for sample values to differ from population values is called sampling error. Sampling error of the mean for any single sample is equal to the difference between the sample mean and the population mean. The greater the sampling error, the less accurate the mean is an estimate of the population. Now, let's consider the figure. Because a sampling distribution is a normal curve, we can also establish its variability. The standard deviation of theoretical sampling distribution of means is called the standard error of the mean. This value is considered an estimate of the population's standard deviation. The curve in Figure 18.2a represents a hypothetical sampling distribution formed by repeated sampling of birth weights, with samples of n equal 10. The means of such small samples tend to vary, and in fact, we see a wide curve with great variability. The curve in Figure 18.2b was constructed from the same population, but with samples of n equal 50. These sample means form a narrower distribution curve with less variability and, therefore, a smaller standard deviation. As sample size increases, samples become more representative of the population and their means are more likely to be close to the population mean. That is, their sampling error will be smaller. Therefore, the standard deviation of the sampling distribution is an indicator of the degree of sampling error, reflecting how accurately the various sample means estimate the population mean. We can use our knowledge of sampling distributions to estimate population parameters in two ways. A point estimate is a single value obtained by direct calculation from sample data, such as a mean. We know that any single value will most likely contain some degree of error as a population estimate. Therefore, it is often more meaningful to use an interval estimate, by which we specify an interval within which we believe the population parameter will lie. A confidence interval is a range of scores with specific boundaries or confidence limits that should contain the population mean. The boundaries of the confidence interval are based on the sample mean and its standard error. The wider the interval we propose, the more confident we will be that the true population mean will fall within it. The degree of confidence is expressed as a probability percentage, such as 95% confidence. We will skip the mathematical calculation for now. Figure 18.4 is a visual representation of 95% confidence interval. The vertical line represents the true mean of the population. The horizontal lines represent a random sample of 100. There are 95 occurrences where the horizontal line intersects the vertical line in 5 occurrences, in bold, where it does not. These 5 samples do not contain the population mean. To increase accuracy, it is possible to calculate a 99% confidence interval. The estimation of population parameters is only one part of statistical inference. How do we know that the effect of a treatment is real and not a reflection of chance? We use hypothesis testing to determine this. Before we can interpret observed differences, we must consider 2 possible explanations for the observed outcome. The first possible explanation is that the difference between the groups occurred by chance as a result of sampling error. This is the null hypothesis, which states that the group means are not different. No matter how the research hypothesis is stated, the researcher's goal will always be to statistically test the null hypothesis. The second explanation is that there is a true difference between the groups and the treatment was effective. This is expressed as the alternative hypothesis. Hypothesis testing will always result in one of 2 decisions. Either reject or do not reject the null hypothesis. By rejecting the null hypothesis, the researcher concludes that it is unlikely that chance alone is operating to produce observed differences. This is called a significant effect, that is, one that is probably not due to chance. When the null hypothesis is not rejected, the researcher concludes that the observed difference is probably due to chance and is not significant. The decision to reject or not reject the null hypothesis is based on the results of objective statistical procedures. However, this objectivity does not guarantee that a correct decision will be made. Because decisions are based on sample data only, it is possible that the true relationship between experimental populations is not accurately reflected in the statistical outcome. Any one decision can be either correct or incorrect. Therefore, we can classify 4 possible decision outcomes shown in the figure on the slide. If we do not reject null hypothesis when it is in fact true, observed differences are really due to chance, we have made a correct decision. If we reject null hypothesis when it is false, differences are real, we have also made a correct decision. If, however, we decide to reject null hypothesis when it is true, we have made an error called a type 1 error. In this case, we have concluded that a real difference exists when in fact the differences are due to chance. Having committed this type of statistical error, we might decide to use a treatment that is not really effective. Conversely, if we do not reject null hypothesis when it is false, we have committed a type 2 error. Here we would conclude that differences are due to chance when in fact the samples represent different populations. In this situation, we might ignore an effective treatment. At some point you will learn more about these types of errors. For now, know that we use level of significance or alpha to help prevent type 1 errors and power, beta, to help prevent type 2 errors. The reading provides more detail. This slide is important for determining what type of statistics to use for an analysis. In addition to determining the type of data, researchers must also determine if parametric or non-parametric statistics should be used. With parametric statistics, there are several assumptions that need to be satisfied. The first is that samples are randomly drawn from parent populations with normal distributions. Therefore, the sample should be a useful representation of population parameters. A goodness to fit test will tell you how well data match the normal distribution. The second assumption is that variances in the samples being compared are roughly equal or homogeneous. This can be tested. The third assumption is that the data is ratio or interval and that mean and standard deviations can be calculated. Non-parametric statistics are used when statistical conditions are not met for parametric. We use non-parametric when normality and homogeneity of variance criteria are not satisfied, for small sample sizes, and when data is nominal or ordinal scale. In lecture this week, you will discuss hypothesis testing. You will also look at the hypotheses of other researchers and practice writing your own.